Welcome to our first video on section 7.1. So this is all about Markov chains. And just a couple general comments before we jump into our video for today. So first comment is that for each of these lectures, I'll be posting both videos and lecture notes. You can choose whether you prefer to watch the videos or whether you prefer to read through the lecture notes, whether you prefer to do both. It's up to you what learning style is going to work for you. Second comment is that we covered about half of this particular section in class on Thursday, March 12th. So if you were in class that day, you might prefer to jump through probably about halfway through this video just to see the new material, or you can watch the video in its entirety just to get an overview of section 7.1. So we're going to start off with that example that we were looking at on Thursday, March 12th. And that example, if you were in class, you might remember, it was about the Clean Hair Shampoo Company. All right, so we're looking from the point of view of this company, and we're thinking about consumers. So consumers are either using our product or they're using a different brand. Let's put our consumers into two categories. Call our categories Y and N. Y just representing yes, meaning a consumer uses clean hair. And let's say N for no represents that a consumer uses another brand. So Y essentially means that someone is our customer, N essentially means that that person is not our customer. So let's look at what's called a transition diagram. We're going to draw a picture here representing how consumers move between being a customer or being one of our customers versus not being our customer, vice versa. So let's think of Y and N as being our two states. We'll just draw them in circles here. We're going to draw some arrows representing the probabilities with which people move between these different states. So let's draw an arrow like this, and let's label that 0.9. So what that means is that if someone bought our shampoo on their most recent purchase, they have a 90% chance of buying our shampoo again. And as soon as you say that, that actually implies something else, which is that they must then have a 10% chance of not buying our shampoo next time. So as soon as you know 90% chance of buying our shampoo, that's 10% chance of not buying our shampoo. Now we could look at people who are not our consumers. So that would be people in the N category. And we could ask, how likely is it that they will stay with another brand? So right now they're with another brand, they're going to stay with another brand. Let's say, for the sake of discussion here, that this is 0.8. So 80% chance that someone will stay with another brand. That then implies that there's a 20% chance that they're going to switch over to our Clean Hair shampoo brand. So let's write an interpretation of at least some of this information, just to make sure that we're comfortable moving from the diagram into wording. So we could say 90% of clean hair customers, or consumers, whatever you want to say there. Let's say 90% of clean hair consumers will buy it again. And that then means that 10% of clean hair consumers will not buy it again. Second piece of information is encoded in the arrows that are coming out of N. You could say 20% of other brand consumers will buy clean hair next time. So let's make sure we got that right. So we're talking about people who are currently using other brands, that's the people in category N, and we're saying 20% of those are going to switch over to being yes. They're going to switch over to buying clean hair next time. 80% of the other brand consumers will stay with another brand. So that's the interpretation. Now, usually the cleanest way to encode this is actually with a matrix. So we're going to write down what's called a transition matrix. And in symbols, if we want to talk about the transition matrix for a given problem, we're going to use the symbol P. It's going to be a square matrix. And what we're going to put in the rows and columns here are the categories. So if we put Y and N in that order, then we need to put Y and N in the same order for the columns. And when you look to the left here, you're talking about the current state. So whether they are consumers now or not, whether they're buying clean hair now or not. And when you're looking over here at the columns of your matrix, you're talking about the next state. So this is referring to whether they will be clean hair consumers next time they go out and buy shampoo. So let's put the numbers in the right places. Looking at the circle for Y here, 90% probability that they will stay Y, 10% probability that someone is Y right now, but they're going to be N next time. And then similarly, if we put the other numbers in the right places, if they're N now, 0.8 probability that they're going to be N next time. 0.2 is the probability that someone is with another brand right now, but that they will buy clean hair shampoo next time. So that's our transition matrix. Key things, you always put the current state in the rows and the next state into the columns. So that is going to be important as we go through a variety of different examples. So next thing we want to do is just define this word in the title, this piece of terminology, Markov chain. And now that we've seen an example, we can make sense of what that word means. So let's come up with a fresh screen here. And we're just going to write down a quick definition in the context of this shampoo problem. So definition, what is a Markov chain? Well, we could say that a Markov chain is a sequence of trials where the probability of moving between states is given by P. And when we say P, remember P was the name that we gave to the transition matrix. So you could say where the probability of moving between states is given by the transition matrix. So let's make this just a little bit more concrete. When we say trials, that's sort of a generic term that would apply to a variety of different examples. But in the example we just did, each trial was a shampoo purchase. So if you prefer just to think in terms of that clean hair shampoo example, you could say it's a sequence of shampoo purchases where the probability of moving between states is given by P. All right, well, when we say given by P, you could say that a little bit more intuitively as just is reasonably predictable. So we have a good sense, maybe from historical data, of how likely people are to move from another brand to clean hair or to stick with clean hair, etc. So sequence of shampoo purchases where the probability of moving between states is reasonably predictable. Those are the kinds of problems that we're going to look at in this section. Doesn't necessarily have to be with consumer goods, could be predicting the weather for the next day, could be predicting stock prices for next week, although that would be incredibly difficult in this current time. But those are some of the types of problems that in general you could apply Markov chains to. So let's talk about a fact, or some facts rather, related to these transition matrices that we were talking about in the previous problem, and we'll just relate these facts back to what we did in the clean hair shampoo example. So let's actually say, let's just label this fact. And what the fact is going to be is 3 properties of a transition matrix. So these properties will apply to any problem, not just the clean hair shampoo problem. So 3 properties we're going to write down. So when we talk about that transition matrix P, first thing is it's square. So when we say square, that means 2 by 2 or 3 by 3. That's just a fancy way of saying it's going to have the same number of rows as columns. And hopefully that makes sense because however many rows you have is how many states you have. And that's necessarily going to be the number of columns as well. So P will always be square. All entries of P are going to be greater than or equal to 0. So they could be 0, they could be bigger than 0, but they will never be negative. And the reason is those numbers in P are probabilities. So that's just like saying we're never going to see negative probabilities. Third property is that each row sums to 1. So if we just flash back to our previous example, maybe let's just focus in on what we had in that bottom row of P. We had 0.2 and 0.8 like that in the bottom row of P. So we're saying each and every row is going to add up to 1. The reason being what this bottom row represented was people who were currently with another brand. And we're saying next time they go out and buy shampoo, they're either going to switch to clean hair or they're going to stick with another brand. But the idea is they're going to do one of these 2 things. So these 2 numbers have to add up to 1. Now the columns actually have no relationship between the entries. So in the top left here we had a 0.9, no meaningful connection between the 0.9 and the 0.1. So it's just a relationship among the rows, or the entries in a given row rather, that are always going to sum to 1. So that's going to be a useful fact as we move forward. So let's put a box around that fact. And then before leaving that idea behind, I'm just going to relate this to what we said with our transition diagram. So let's just flashback to the transition diagram that we had in the previous example. And I'm just going to focus in on the circle for yes here. So we said that 90% probability a clean hair consumer was going to stick with clean hair. And that implied that there was a 10% chance that they were then going to switch to another brand. So if we focus in on this third fact here, the fact that each row sums to 1, and if we tried to make a parallel with that and relate that to a transition diagram, then we could come up with a second fact here. We could say in a transition diagram, we're talking about the sum of the arrows leaving each state is 1. So in any transition diagram, the sum of the arrows leaving each state is 1. We might even want to draw the information for n here. Remember it was 0.8 there and 0.2 there. And you can say that these numbers, 0.8 and 0.2, are just another way of rephrasing this bottom row of the transition matrix. So if each row of a transition matrix sums to 1, and you rephrase that in terms of a transition diagram, in each transition diagram, the sum of the arrows leaving each state is 1. Whereas there's no meaningful relationship between the sum of the arrows entering a state. It's all about leaving a state. Great, so with that, let's move into a new example, and we're going to try to figure out what our consumer base looks like right now. Let's start a fresh page here. So at this point, we know the probabilities of moving between different states, but let's say we wanted to know what was going on right now. So we would call this an initial state matrix. In symbols, we're going to call that S sub 0. So the 0 just references what's happening right now. And it's just going to be a single row. It's going to have the categories in the same order as you had them on the transition matrix. So Y and then N. And let's put some probabilities in here. So let's say someone told us that S0 was equal to 0.4, 0.6, like that. So the interpretation is that 40% of consumers use clean hair right now. So S0 is a statement about what's going on right now. And these numbers in this row are representing the probabilities that someone is in a given state. So 40% of consumers are in the yes state, 60% of consumers are in the no state. That's right now. Now let's jump ahead one shampoo purchase. So then we'd be looking at, in words, you'd call it the first state matrix, and in symbols, you'd call it S1. So notice that S0 represents what's going on right now. S1 is actually talking about what's happening one time step from now. So one shampoo purchase into the future, what's going to be happening? Well, the way we're going to calculate that, we're going to start with our initial state matrix, which was S0, and we're going to multiply it by P. So what our transition matrix P does is it multiplies with a state to actually take us into the next state. All right, so starting state was 0.4, 0.6. And let's multiply by our transition matrix. So just remember what that looks like. Was 0.9, 0.1, 0.2, 0.8. And we're just talking usual matrix multiplication here, where you circle the row of the first matrix, you circle any columns of the second matrix, and you're doing your dot product operation. So if you haven't quite figured out matrix multiplication yet, I would recommend that you go back and look at the videos on the website. There are a few videos for matrix topics. They're located right at the bottom of the website if you're interested. All right, so doing our matrix multiplication here, we would find 0.48 and 0.52. And the categories are Y and N, same order as they were in all our previous matrices. So what this is giving us is our percentages after the next purchase. Or you could say one purchase into the future. Everyone uses up their shampoo, goes out and buys their next shampoo selection. Now how many people are using clean hair? Well, 48% of people. If you wanted to look 2 purchases from now, you could call this the second state matrix. So you're looking 2 states into the future. In symbols, you would call that S2. And the way you'd get that S2 is you'd take S1, so your previous state, and multiply it by P. So we would use the 0.48, 0.52 that we just calculated. We would multiply that by P. So same familiar P, the 0.9, 0.1, 0.2, 0.8, and you can get a little bit more practice with matrix multiplication. Check this on your calculator, comes out to 0.536 and 0.464. Again, those categories, if we want to label them, or the states, you could call them, the Y and N. So 2 purchases from now, about 53.6% of people, or about 54% of people, are using clean hair shampoo. So this is really good for clean hair. Seems like their market share is going up. All right, so one fact that we can conclude from this previous discussion here is that if you want to figure out any state, say SK, what you need to do is take the previous state and multiply that by P. So if we were writing this down generally with a formula, you'd say to get SK for any number K, you'd need to look at the state that is one smaller than that, one number smaller than that, times P. So usually the best way to make sure that you understand these kind of facts is just to see, okay, am I comfortable plugging in a number? If I wanted S97, for example, 97 shampoo purchases into the future, then I'd have to take S96, which I would have previously calculated, and multiplied that by P. So that's what that's saying. Similar fact, or related fact, let's say, while we're still on this page and we've got things to look at. This is a second fact about state matrices. Let's say in any state matrix, the entries sum to 1. So we'll just put a box around that to separate that from our previous fact. So look at any of the state matrices that we've looked at here, like the 0.4, 0.6, or even something more complicated like this one. In any of these state matrices, the numbers are going to add up to 1, and that's because they're probabilities. In this example, they're talking about market share. So the market share between Clean Hair and the other brands, it's always going to add up to 100%, or it's always going to add up to the number 1. Okay, so let's start a new screen, new idea here, and we're going to think about a second way of calculating these state matrices. So new page. Let's notice a different way of thinking about these state matrices. So you could say S1 is equal to S0 times P. You could say S2 is equal to S1 times P. That's what we said in our previous screen. But if you now use the fact that S1 is S0P, then you would end up with something like S0P times P. And it would be quicker just to call that S0P squared. If we did the same thing for S3, we'd say, well, S3 is S2 times P, S2 being S0P squared times P. So maybe you can see where this is going. S3 could also be written S0 times P cubed. So that gives us a different way of thinking about SK. You could say SK is going to be S0 times the appropriate power of P, whatever the subscript K is there. So again, to make sure that you understand this fact, you can try just plugging in some interesting number. Make sure you're comfortable with that. So if you wanted to figure out 17 shampoo purchases into the future, you wanted S17, you could say that's S0 times P to the power 17. So we've now got two different ways of calculating those state matrices, and depending on the problem, one might be more useful than the other. All right, so let's switch gears. I'm going to do a different example now, moving away from Clean Hair. So this is just going to be a shorter conceptual example. Let's say someone gives us two different powers of P. So we don't know what P is, but we do know what P squared is, and we are told what P to the 6th is. So let's put some numbers in here. Say P squared is 10, 0.75, 0.25. And we don't even know what the problem is here. We don't know if we're talking about shampoo or weather or stock prices or what, but someone just tells us, hey, there's two states that are possible. We're going to call them A and B. And if you multiply P by itself, this is the matrix that you're going to get. Similarly, if you multiply P by itself 6 times, and you can imagine here that your states are labeled AB, AB, the numbers we would get, let's say we're told it's 1, 0, and actually I'm going to write some bigger numbers here, so I'm just going to make a bit more room over on this side to make my matrix a little bit easier to read. So let's say in the bottom row 0.9844, let's say, and 0.0156. All right, so that's all given. The question is, what's the probability of, let's say, going from state B to state A in 2 trials? And then as a follow-up, same question for 6 trials. So it will be quick to find our answer, but we're now just thinking about these transition matrices in a more conceptual kind of way. All right, so on the surface, this might seem complicated. If we were talking about shampoo, we'd be saying we're not interested in the next purchase. We're interested in what people are going to do 2 purchases from now. So that seems a little complicated, right? But to figure that out, based on our fact back here, to figure out what's going on, k states into the future, it's really the matrix P to the K that's going to describe that transition. P to the K is going to describe how you move from your starting state to your state, K states into the future. So if you want to know what's happening over 2 trials, the answer is look at the matrix P squared. P squared is encoding what's happening over 2 trials. And what we're interested in is going from state B. So remember, our current state, always expressed in the rows, our future state expressed in the columns. So meaning we're interested in this number right here. Whatever that number is going to be our answer. So the answer is, if we look up at P squared and choose that position, 0.75. So 75% chance that we go from state B to state A in 2 trials. We don't care about what's happening on the next trial. That's already encoded within this matrix. So to answer the question for over 6 trials, we need to look at the appropriate power of P. P to the 6 is going to encode how we're moving from an initial state to a state that's 6 states in the future. So think of P to the 6 as jumping us forward 6 states in time. And again, we're interested in the probability of moving from state B to state A. So just choosing the correct position in the matrix, we're going from B to state A in the future. We need to choose whatever this number is. So the second part of the answer is 0.9844. So that's just a little bit of conceptual reasoning to make sure we understand what these powers of P really represent. So they jump, P to the K jumps us forward, K states in time would be a nice summary of what we said there. So to finish off this section, we're going to do one bigger example, just touch on a lot of the key ideas that we've talked about here, but through the lens of a new problem. So here's our last example. Let's say we're going to talk about stock prices. All right, imagine that we're talking about, just for simplicity, imagine that we're talking about a single stock. So you can imagine whatever publicly traded company you like, whatever your favorite publicly traded company is, let's think about that, and let's think about tracking its stock price. So let's say if the price increases one day, so if it increases on a given day, let's say the probability that it increases the next day is, let's say we know from historical data that it's 0.65. So if the price increases over the course of one day, probability that it's going to increase over the next day of trading, 65%. So that's one piece of information. Now we're going to say similar kind of sentence, but with a few key differences here. So if the price decreases one day, we need to have a sense of what's going to happen. Let's say the probability that it decreases the next day is, well, let's say it's 0.45. So if the price has a bad day one day, it decreases over the course of the day. Probability that it's going to have a bad day the next day of trading, 45%. First thing we're going to do here, let's draw a transition diagram. So we'll think back to our clean hair shampoo company example and just try to do something similar. Well, what would be important here is just naming the states, just for your own clarity and the clarity of anyone reading your work. We should come up with some names. So maybe it would make sense to go I for increase and D for decrease. And we're just going to draw a diagram that looks like this. So our two states are increasing and decreasing. Increasing and decreasing. So I and D, not I and N. Okay, increasing and decreasing. And then let's start to draw some arrows. So if the price increases one day, probability that it increases the next day, 0.65. And because the arrows leaving each state have to add up to 1, we know without too much thinking that that's going to have to be 0.35. If there's a 65% probability that it increases, that means 35% probability that it decreases. Okay, now completely separate information is what happens if you're looking at a stock that has decreased today. So if it decreases on one day, jumping ahead to the next day, probability that it decreases the next day, 0.45, that was given in the question, and therefore 55%, or let's say 0.55, probability that it increases the next day. So the sum of arrows leaving a given state will always add up to 1. Okay, based on that, let's turn that into a transition matrix. So if we wanted to give our transition matrix a name, we'd call it P. Always a good idea to label our categories. And whatever categories you use for the rows, you should really do that for the same order for the columns. So if you go I and D here, you have to go I and D there. If you decide to go DI, fine. Then you just want to go DI for the columns as well. Keep it consistent. And just remember that what happens here in the rows is representing your current state. Since we're talking about days of trading, our time interval is a day. We would say this is the current day, and this is the next day. Now, a bit of an aside here, but time intervals can be chosen however you like in a problem as long as you use them consistently. So someone else might be saying, oh, I don't care about daily fluctuations in price. I'm just going to look at what happens week over week. So that person could say the rows represent the current week, the columns represent the next week, and then all the phrasing of the question would involve what's happening week after week after week. In this case, we're talking day after day after day. So that's an important thing to realize, is just what your actual time step is. So current day and next day, and let's fill in the numbers. So this I here represents stocks that have increased today, 0.65, probability that they're going to increase tomorrow, 0.35 probability that they're going to decrease tomorrow. For stocks that have decreased today, 0.45 probability that they're going to decrease again tomorrow, 0.55 probability that they will increase tomorrow. So I'm just going to make that slightly easier to read. That's a 0.45. Okay, that's our transition matrix. So last question here. We're going to do a part C related to this, and I think do that on a fresh screen. Okay, so part C. Let's say there's an 80% chance that the stock decreases today. So suppose that you're looking at this stock before the market even opens, so we don't know yet what's going to happen today, but somehow we've decided that there's a pretty good chance that the stock is going to decrease today. So there's an 80% chance that the stock decreases today. We want to find the probability that it increases. Okay, probability that the price increases 2 days from now. So when I say 80% chance that the stock decreases today. I mean the stock price. So 80% chance that the price decreases today, probability that the price increases 2 days from now. So if we can answer this, I would say we understand the basics of Markov chains. All right, so we're being given some information about what's going to happen today. So today is our current time, that's the current state that we're in. If we were giving that a name, we would call that S0, and we're writing things in the order I and D. So 0.8 is the probability that the price decreases today. And remember that the entries in a row are always going to sum up to 1 because they're covering all the possibilities. So that means 20% chance that the price is going to increase today. Okay, that's what's going on today. Now let's think about what we want. We want to know what's going to happen 2 days from now. Our time interval in this problem is a day. So when we say 2 days from now, that means we want to look 2 states into the future. So 2 states from now, you could say. And the symbol you would use for that is S2. S2 is 2 states from now, 2 days from now. So based on our previous facts, you could think of this as S1P. That would be fine. Then you need to calculate S1 along the way. Might be just a little bit more direct instead to say this is S0 times P squared. So P squared is going to jump us 2 states into the future. All right, so let's do this calculation. So here's our S0. We need to multiply that by P and then by P again. So that's what we mean by P squared. Multiply P by itself, and then multiply by S0 in the order S0 times P times P. Okay, so let's put all our information in. Just thinking back to the previous screen, our information there, we had 0.65 and 0.35. And then 0.55, 0.45 was our transition matrix. And we're going to copy out that same transition matrix again. So the 0.65, 0.35, 0.55, and 0.45. Great. So let's just finish our calculation up here. So you can think about multiplying 0.2, 0.8 times this matrix P here. You could do that first and then leave the last one for the end. Or equivalently, you could multiply these guys together and just keep the S0 out in front. Doesn't really matter which way you do it. I'm just going to say 0.2 times 0.8. Let's leave that alone. And let's just, for the sake of practice, let's practice multiplying P times P. So you'd circle the rows of the first matrix always and the columns of the second matrix. We're going to do our dot products and just see what this comes out to. So 0.615, 0.385 is our top row, bottom row 0.605, and 0.395. And if you feel like doing a little double check here, if you're just unsure about the numbers, remember that the rows should add up to 1. So if you're seeing that, that's some evidence that you're on the right track there. And then last multiplication to get our answer, circle the rows of the first matrix, columns for our second matrix, and do our dot product. So here's our close to our final answer coming up as we do this calculation. So comes out to 0.607 and 0.393. And the order will always be the same. The order of the states is always the same as whatever you decided earlier in the problem. So in this case, it would be I and D in that problem, in that order. So to answer the question, what's the probability that the price increases 2 days from now? Well, we make sure that we're looking at S2, which we are. This quantity here is giving us S2. And then to figure out the probability that it's increasing, we're just looking at the correct entry in the matrix. So that's our answer, 0.607, or you could say 60.7% probability that this stock is going to increase in price 2 days from now. So that's the basics of Markov chains. Thanks for watching.